January 1954. A sleek British jet climbs into a clear Mediterranean sky, carrying passengers who believed they were riding the future. Minutes later, that future tears apart in midair. What failed was not a pilot, not a single part, not one dramatic mistake. What failed was an idea that seemed perfectly reasonable at the time. If a metal fuselage survives one pressurization cycle, and then another, it will keep surviving. The de Havilland Comet proved that assumption wrong, and it changed aviation forever. To understand why, we have to step back into the early 1950s, when commercial flight was about to make a leap. Before the Comet, most airline passengers flew in piston-driven aircraft. They were slower, noisier, and rougher at altitude. The Comet promised something radically different, a pressurized jetliner that flew higher, faster, and smoother than almost anything in civil service. And visually, it looked like tomorrow. Clean lines, buried engines in the wing roots, a quiet cabin by the standards of the day. For Britain, this was not just another airplane. It was a national symbol of engineering leadership in the post-war world. When Comet service began in 1952, it seemed to confirm the dream. Passengers loved it. Airlines saw prestige. The jet age, it appeared, had begun under British control. Then came warning signs. The Comet fleet experienced serious accidents early in service. At first, investigators did what investigators always do in real time. They looked at weather, operations, procedures, and specific events. Some losses could be explained by local conditions and operational factors. But then a new pattern emerged, and this pattern was harder to dismiss. On the 10th of January 1954, BOAC Flight 781 departed Rome for London. It never made it. The aircraft broke up over the Mediterranean near Elba. There was no long distress call, no classic gradual failure sequence. It came apart quickly, in cruise. The response was immediate but cautious. Authorities grounded comets, reviewed available evidence, and introduced modifications aimed at likely contributors. Then the fleet returned to service. And then it happened again. On the 8th of April 1954, South African Airways Flight 201, another Comet, also broke up in flight over the Mediterranean. Different operator, similar catastrophe. At that point, the statistical argument was over. This was not random noise. Something systemic was wrong. The Comet 1 fleet was grounded again, this time with far greater urgency. Now the investigation became one of the most important engineering inquiries in aviation history. British investigators, including teams at the Royal Aircraft Establishment in Farnborough under Sir Arnold Hall, approached the problem with unusual rigor for the era. They did not settle for theory. They built evidence in layers. First, they recovered wreckage from the sea floor. That alone was a major operation. In an age before today's digital forensic ecosystems, physical reconstruction mattered even more. Investigators mapped pieces, studied fracture surfaces, and searched for signatures of overload versus progressive cracking. Second, they recreated the stress environment of the aircraft, repeatedly under controlled conditions. A complete Comet fuselage was placed in a large water tank and subjected to pressure cycles to simulate repeated cabin pressurization and depressurization. This was the key move. Because the Comet's danger was not a single huge load event, it was cumulative damage, tiny crack growth, cycle by cycle, almost invisible, until suddenly catastrophic. Every time a pressurized aircraft climbs, the cabin pressure rises relative to thin outside air. That pressure difference pushes outward on the fuselage skin. On descent, the load eases. Over years of service, the structure experiences thousands of these cycles. If stress is evenly distributed and details are robust, the aircraft can tolerate that life safely. If local stress is concentrated at sharp geometric features or poorly distributed joints, fatigue can initiate. Fatigue is deceptive. Engineers sometimes describe it as a story written in microscopic increments. A crack begins where stress is highest. It grows a little under each cycle. At first, growth can be slow enough to seem harmless. Then, once the crack reaches a critical size, remaining material can no longer carry the load. Final failure can be extremely rapid. That is what the Comet investigation revealed. Several design details created high local stress concentrations, especially around cutouts in the pressurized fuselage. Square or near-square window geometry and certain apertures gave cracks places to start and directions to run. Rivet hole quality and local manufacturing detail also mattered, because fatigue is sensitive to tiny imperfections. The most famous visual lesson came from the windows. Corners concentrate stress more than smooth curves. A rounded shape spreads load. A sharper corner focuses it. Under repeated pressurization, that difference becomes life and death engineering. In modern terms, you could call this a gap between static strength thinking and full life cycle damage tolerance. A structure can pass static load tests and still fail in service if cyclic loading and stress concentration are underestimated. The Comet did not fail because engineers of the time were careless. It failed because a frontier technology met a frontier unknown. The jet age moved fast, and fatigue behavior in pressurized, high-altitude commercial operations had not yet been fully mapped by experience. But once the mechanism was understood, aviation did what good engineering cultures do. It changed methods, standards, and assumptions. Aircraft design shifted harder toward fatigue, life analysis, fracture mechanics, and fail-safe philosophy. Details around windows, doors, hatches, and cutouts were reevaluated with new seriousness. Inspection philosophy evolved. Test philosophy evolved. Certification philosophy evolved. Instead of asking only, can this structure survive the maximum expected load today? Engineers increasingly had to answer, how does this structure age after thousands and thousands of cycles, and what happens if a crack starts anyway? That second question defines modern airframe safety. The Comet story is also a systems story. Design choices, test programs, manufacturing details, maintenance assumptions, and certification frameworks are not separate worlds. They are one chain. If one link is optimistic and another is under-instrumented, risk can compound quietly. And this is why the investigation itself became so influential. The water tank pressure cycle tests were not just a technical exercise. They were a cultural milestone, a public demonstration that if the mechanism is uncertain, you build experiments that force reality to answer. It is hard to overstate how much this mattered for the industry that followed. Later, jetliners, including the improved Comet variants, incorporated major structural changes. Window geometry became more fatigue-conscious. Structural details were strengthened and refined. The broader industry absorbed these lessons and pushed them into standards. Over time, jet travel became one of the safest large-scale transport systems in history. Not because early designs were flawless, but because failures were investigated deeply and lessons were institutionalized. There is also a human dimension we should not ignore. For passengers in the early jet era, trust was fragile. Public confidence can collapse faster than any structure. The way to rebuild it is not marketing language. It is engineering credibility, transparent findings, hard redesigns, and disciplined verification. The Comet forced exactly that response. If you zoom out, the deeper lesson is not avoid innovation. It is the opposite. Innovate boldly, but assume your first model of reality is incomplete. When a system is new, unknown failure modes are not a possibility. They are a certainty. Your job is to reveal them before service when you can, and to detect them quickly if reality still surprises you. That is the engineering maturity the Comet helped create. Today, when a modern airliner window looks softly rounded, it looks ordinary. But in that ordinary shape is a hard-earned memory. Stress does not care about elegance, reputation, or optimism. It follows geometry and cycles. And when modern certification requires exhaustive structural fatigue evaluation, that too is part of the same legacy. Engineers learn that safety is not a one-time proof. It is a life cycle argument, continuously defended by analysis, testing, inspection, and feedback. The Comet was the first commercial jetliner to carry the world into a new era. It was also the aircraft that taught the world what that era would cost in engineering truth. Not because jet flight was impossible, because jet flight required a new level of honesty about how materials fail over time. So what really happened? A beautiful machine met repeated stress at vulnerable points. Microscopic cracks became macroscopic fractures. 2 catastrophic breakups forced a full rethinking of fatigue design. The investigation identified the mechanism, The industry redesigned the details, and commercial aviation crossed a painful but essential threshold. Why did it fail? Because the structure was designed for the loads engineers expected, but not fully for the damage those loads could accumulate. What changed afterward? Almost everything that matters. How we model fatigue, how we shape cutouts, how we test pressure vessels, how we certify airframes, and how we treat uncertainty in complex systems. And that is the final takeaway. Engineering failures are rarely just stories of broken metal. They are stories of assumptions under stress. The de Havilland Comet broke in the sky, but its real impact was on the ground, in design offices, test facilities, and certification rules across the world. It did not end the jet age. It taught the jet age how to survive.